So we are gonna do most of the first unit of calculus for next year to benefit those of you that are going on if you're gonna take calculus in college. And the first thing we look at are limits. Limits are behavior of a graph. It's not where a point actually is, it's just behavior. So before I start writing on here, here's the big old pep talk and the analogy that I use. Have you ever been walking up the stairs and you're not paying attention and you get to the top of the stairs and you take another step anyway, and you trip and fall and drop everything and all your friends laugh at you? Do you know what I'm talking about? Like, have you ever tripped up the stairs? There's not a step there, but if there was, your foot would have landed right on it. That's like a limit. It doesn't matter if there's actually a point in the graph. There could be a hole there. It's just where the graph was headed. Do you get what I'm saying? It's like falling up the stairs. That's what you want to remember. Now, what we're going to do is look at this one, and I'm just going to do the calculator button pushing for us. So just watch, okay? I typed this into y equals, and we're going to go to the table. Now, I'm going to go to my table set. If you never knew how to set your table, I'm going to show you right now. Do you see this button that says table set right there? How do I get to that since it's above the button? Okay, so I'm going to hit second window, table set. I'm going to start it at -2 because that's where I want to be centered on the table. So I'm going to start at -2. And this delta table, delta is a triangle. That's the Greek letter delta. It means change in. Physics people, do you know, you are very familiar with delta? Okay. So I want to count by 0.5. And now I'm going to hit this button for table. So second graph is going to give me my table. And here we go. What does it say at -2? Error, but that doesn't matter. Remember, it's like falling up the steps. It's just behavior. We're going to put error there for that one. And we're going to need to round off our decimals. But on either side of that, at -2.5, do you see how we have -1.4? That's what's going to go right here. I'm going to do all the button pushing for us. You just have to watch. And then for -1.5, we get -0.714. Now, what we're going to do is bring that in. When you guys do labs in science, do you ever use microscopes? Do you ever use this? Do you know you don't use microscopes in your labs in science? What are they for then? Do you know what the zoom on a microscope is though? How it would zoom in on something? That's what we're gonna do. We're gonna zoom in on this point here. So I'm gonna go back to my table set, restart it at -2. But how would I bring it in? Instead of counting by 0.5, what do I want to count by to bring it into this next one? 0.1, good. So I'm gonna change that to 0.1, go back to our table, and then we can get what's on either side. So at -2.1, that's going to go in this box right here. We got -1.069. And then for -1.9 on the other side, I got -0.935. And now I want to bring it in a little bit further. We're zooming in super, super tiny. So I'm going to go back to the table set, restart it at -2. What do I want to count by now? What do I want my delta to be? 0.01. So 0.01, go back to my table, and now we can see what's on either side. And that's far enough. I mean, you could keep on zooming in if you want, but on this side, we got -1.007. And then on this side, we got -0.993. So here is the whole point. If you keep zooming in, this is going to go -1.00000 something, and this is going to go -0.99999 something. What are they both headed towards? Even though there's not actually anything there, what's the behavior of both sides headed towards? -1 is the answer. You still get an answer even though there's an error there, as long as both sides come to the same place. As long as when you zoom in, they both go together. You've actually done this before. If I cover up this word limit, what does it feel like? Use your instincts. What does it feel like you should do with that? Factor it. Draw your two sets of parentheses for the numerator and the denominator. You've done this before. If I cover up the limit, it becomes an algebra problem. Ready? Look, calculus, algebra, calculus. Cover that up. Now it's algebra. All right. This is going to split x and x, and then what? One and two. Good job. Pull this out of you like pulling teeth. All right. And then to get a +1x in the middle, what symbols are we going to need? -1 plus 2. 2 minus 1 is 1, is what happened there. And then you're going to do the same thing on the bottom, x and x. How is 10 going to split? 5 and 2. And they'll both be plus, because 5 plus 2, 7. Good job. All right, what cancels? That is where the hole in the graph is. We did this back in the rational unit. You all did really well with it. Cancel that out. And the reason it's -2 comma something, see how we were approaching -2, is because -2 plus 2 gives you 0, and you're not allowed to divide by 0. That's why that happens. Now, how do you get the other part of the whole? You take -2 and do what with it? Look back in. So what's left here? So let's see, -2 minus 1, that's -3. Try to just hold that in your head. -2 plus 5, 3. So if you have -3 over +3, that's where the hole is. And you still get an answer. That's still the answer, even though there's a hole. Because again, it's just behavior. It's like falling up the steps. All right, so in order for a limit to exist, we got 3 things. The first is the same value is approached from both sides. So both sides have to come together. If one goes up here and the other goes down here, there's not a limit. Now you have to zoom in and get them both to come to the same place. Unless it's a one-sided limit, which I'm going to show you. If it's one-sided, you only need to look at that one side. All right, second thing, your graph does not increase or decrease without bound. I'll explain that. Well, what do you think without bound means? If something does something without bound, what does that mean? It goes on forever and ever and ever, okay? So it means it doesn't go to positive or negative infinity. Again, unless it's one-sided. If it's one-sided, then you can answer that question. But if otherwise, if it goes up and down forever, you can't get an answer. And then the last thing is that the graph does not oscillate. And I'm going to show you what that means. Let me type in another graph here, make sure I'm in the right mode. So I'll show you what oscillating means. So I just typed in a function. Do you see what's going on there at 0? You should be confused. Are you confused? Should be. Okay. So let me zoom in. It's going to look sort of like a little heartbeat machine. Do you see what's going on there? All right. But if I zoom in again, can you tell what exactly is going on at 0? No, it's because the graph is sort of just freaking out. Here, I'll zoom in again. It's going to just look like a barcode. Oscillating means it's like jumping around like this. So there's no overall behavior. Do you get what I'm saying? See, it's sort of just freaking out. Like, anyway, that's what oscillating is. So there's no defined behavior. Remember, a limit is behavior. If there's no defined behavior, like they both come to the same place, then you don't get a limit. So anyway, that's what oscillating is. So we are going to use this lovely graph to answer the questions. This is entirely, look at it, there's the answer. So you are going to have to watch me point to stuff because I don't have a better explanation than, hey, look, this is what it is. There's not any work to these. So you're going to have to watch, okay? This says limit as x approaches what? -1. So make sure you're reading with me, all right? So what we're going to do is we're going to find -1 on the x-axis. Do you see that right there? Do both sides come to the same place? Yes. And what is that value that if we zoom in on -1, but do both sides go? 0. Good. That's the answer. 0. Don't think too hard about it. If you're like, that's it. Yep. All right, let's do the next one. Limit as x goes to 1 of the function. So you find 1 on the x-axis. You're going to have to just look where I'm pointing. Do you see that? 1. Do both sides come to the same place? Even though there's a hole, it doesn't matter. What do both sides approach? -1 is your answer. Doesn't matter that there's a hole. Both sides go to the same place. If you zoom in on it, that's your answer. Now, see how this is -6 with a little plus sign? That means -6 from the positive side or from the right. You actually have seen this before. Do you remember back when we did logarithms? Sort of. Some of you are nodding your head. That's good. Remember there was an asymptote and we approached it just from the one side and I put in a little, okay, good. You guys remember, perfect. You listened to me. So we're going to approach -6 just from the right. So here's -6. If you approach just from the right, where is that headed? -infinity. Now you're allowed to put that because it's one-sided. You can only get away with that if it's one-sided. So number 4, -6 from the left. Well, here's -6. As you approach from the left, it's again -infinity. But here's the thing. This one says limit as x goes to -6 overall. Is there a from the left or from the right? No. And are these two arrows ever going to touch? Will they ever meet? No. So you have to put DNE, which does anyone know what that stands for before I tell you? It does not exist. Good. Does not exist because these two arrows are never going to touch. So they're never going to come to the same place. All right, let's try it again. -2 from the which side? Left. Okay, so find -2 on your x-axis. It's right here. You're going to have to just watch me point to it. We're only going to go from the left. That's only this side. I know there's a hole there, but it doesn't matter. As we go from the left, what y value is getting approached? -1 is your answer. It's all you got to do. You just got to get good at reading a graph. All right, -2 from the right. So look, here's -2. If we approach just from the right, we're approaching this point. Can we call that 2? Like, I know it's a little bit above 2, but can we call that 2? Just pretend. All right, we're going to say 2 for that. And then this one is limit as x approaches -2 overall. So do both of those come to the same place? No. Do you see how one goes to -1 and the other one goes to 2? There's a jump there, so I'm going to put does not exist. If they don't meet up, picture me doing this. If they don't come to the same place, then you don't have a limit. Oh, you've done these before. This is just end behavior. Limit as x goes to -infinity. If you look at the left side of this graph, where is it leveling off at? 0. And do you remember me saying over and over and over again, will it ever touch 0? No, but it is behavior. That's what a limit is. All right, limit as x goes to +infinity. So you're going to look at the right-hand side. Where is this leveling off? -2. It won't ever actually touch -2, but that doesn't matter. It's just behavior. All right, this one is 4 from which side? From the left. Good. So we're going to find 4, which is right here. From just the left, where are we headed? -infinity. And then 4 from the right is +infinity. And so what is 4 overall? Does not exist. Good. All right, this is -5 from the, which side? Negative side, from the left. All right, so -5, let me find that. Here's -5 from the left. Actually, it could be from the left or the right. It's not going to make a difference. What number is being approached if we approach -5? Yep, -2. And then limit as x approaches 5. Now there's a hole there, but does it matter? No. Do both sides come to the same place at 5? Yes. And what value is it? 0. What I tell people to do if they feel like they're getting overwhelmed by all the arrows and mess of the graph is cover up everything except the value you're looking for. Like if you just want to look at 5, cover up all of this except 5. All right. I'm going to grab another sheet. Can I just borrow yours? Thanks. So I don't have to keep flipping this over and over. Now this says find the actual functional value. That's not behavior. That's is there actually a point there? This is not calculus. This is just algebra. So let's do f of -2. And you can just look up here at mine so you don't have to keep flipping it over. So f of -2, where is the actual point? The filled in point, where does it exist? 2. We're going to call that 2. Do you remember piecewise functions? We did this with piecewise functions back in unit 2. All right, how about -6? What do you think? Asymptote. So we're going to say DNE. or undefined. All right, how about 1? Good. That's tricky. That's like, haha, I tricked you. I stole the point. Now it's over here. Do you see how it got moved? It's up there. Floating point at 4. The limit is at -1. Both sides go to -1. The behavior is at -1, but the actual point's up there at 4. We're going to talk about that more in a minute. All right, how about 5? Danny? How about 4? Okay, asymptote. So we're going to say does not exist. F of 0, where's the actual point? -1. And then f of -1, 0. All right, so now we're going to talk about continuity. And we've talked about continuity before. Do you remember removable and non-removable? Because we're about to have that whole conversation again. And I described it as you can't lift your pencil off the paper. Like if you can trace it without lifting your pencil, then it's continuous. We're just going to make a much more formal definition here. So there's 3 parts to the definition. In order for a function to be continuous at a value c, first of all, f of c exists. Again, we're using c here for the like in general terminology, but when you do a problem, that'll be a number. It'll be like f of 3 exists. What that means is there has to be a point there. That should hopefully be intuitive. Like if you want there to be continuity, something's got to be there, right? You can't have a hole, right? Second part of the definition, the limit as x approaches c of the function also exists. That means that the same value is approached from both sides. There has to be behavior. If one side goes up here and the other goes down there, then you've got to jump and it's going to be discontinuous. And then the last one, bless you, is that those 2 things are the same. So what, because writing that and writing that usually goes fine. And then when I do the third one, everyone loses their mind. I'm going to get rid of these words exists, and I'm just going to put an equal sign in between here, right? So the point f of c equals the limit as x approaches c of the function. So that's like, you can't steal the point and put it somewhere else. So like there is a point and there is a limit, but they don't equal each other. So I'm going to show you what it looks like when we break all these rules. So those are the 3 rules. Let's think of ways we could break the first rule. There's 2 ways you could, we're going to be rule breakers here. How could you make there not be a point? There's 2 ways you can do that. An asymptote is the first one, and a hole. Good. So that would be f of c does not exist. Both of those situations. You have an asymptote or you have a hole. All right, let's think of ways we could break. Well, actually, there's only one way you can break the second rule. The way that you wouldn't have a limit, kind of just introduced limits to you, but does anyone want to have a go with that? How could you break the second rule and have there not be a limit? What would it look like? Does anyone know what we call this? If it does something like that? It's a jump discontinuity. Good. So that would be when the limit as x approaches c of the function does not exist, because both sides don't come to the same place. So like there is a point, but there's not a limit. And then the third rule, you have a point and you have a limit, but if they don't equal each other, it looks like this. It's when you like just stole the point, like took it out and put it somewhere else. So that's when the point does not equal the limit. A lot of these are intuitive and it's not difficult to understand. What gets everybody is the notation and how to write it, because I get that that just looks like a whole bunch of symbols. The familiarity comes with just doing a bunch of problems. So you just have to practice writing it. And I want to just go through real quick and describe them as removable or non-removable. I won't make you write it, but let's just do it verbally. An asymptote, what would that be? Non-removable. How about a hole? That's removable. You just removed a point. So let's review. This one is non-removable. This one is removable. All right, how about a jump? Non-removable. You can't fix it just by putting a point back. That's non-removable. And this one is removable because you just remove the point, right? So these two are removable if it's a whole. These two are non-removable. It's a bigger problem. All right, let me borrow your paper real quick. So we're going to use the previous graph. So I'm going to flip this back over. You don't have to do that. I'm just doing that so that we can still see it. And for these, we're going to state yes or no if the function's continuous there. And if it's a no, we're going to give a reason why. All right. So let's look at 4. And you'll have to look up here so you don't have to keep flipping your paper over again. So at 4, first of all, do you think continuous or discontinuous? Just yes or no is what I'm looking for. At 4, okay, no. At 4, no. You want to go through the rules in order. Is there a point? Is there a limit? Do they equal each other? So let's go through them. Is there a point at 4? No. So the easiest way to write it is f of 4 does not exist. The rules kind of go easiest to hardest. So the first rule is the easiest one to explain. There's just not a point there. All right, how about -2? Just yes or no, use your instincts. Continuous there, yes or no? No. Good. Now we'll go through the rules. Is there a point at -2? Yes. So the first rule is good. There's not a limit because the two pieces don't come to the same place. Do you see what I'm saying? All right, so here's how you write it. Limit as x approaches -2 of the function does not exist. There's not a limit. The limit as x goes to -2 of that function does not exist. And again, that's what gets people. The no is fine. People look at it and they're like, oh, no. You know, your instinct is going to tell you that. It's just difficult to write. All right, how about it 3? Here's 3. What do you think? Yes, we're continuous there. So we caught a break. We don't have to say anything if it's a yes. How about -6? No. Is there a point at -6? No. So we would say f of -6 does not exist. Not a point there. Cool. You guys are handling this. How about 5? Yes or no? Also a no. And what's the easiest way to say it? Yep, good. F of 5 does not exist. Actually, you couldn't say that any other way because there is a limit. Both sides go to 0. There's just not a point. All right. How about 1? Look at 1. What do you think about 1? Yes or no? For continuous at 1. No. That's correct. Let's go through the rules. Is there a point for 1? Yes. Is there a limit? Do both sides come to the same place? Yes. The problem is that third rule. The point and the limit don't agree with each other. So you're going to write f of 1 does not equal, it's like the no parking sign, like the line through, limit as x approaches 1 of the function. Now these last ones are intervals, so it needs to be continuous on the entire interval. So this one is from 8 to infinity. Watch me point to it. Here's 8. Onwards forever. Is this graph continuous from 8 onwards? Yes. You can trace it without lifting your pencil off the paper is the easiest way to put it. All right, -5 to -2, but they're parentheses. Does that mean that we're including them? No. So if you just look from -5 to -2, are we continuous everywhere in between there? Yes, and the fact that there's a hole at -2 doesn't matter because we have a parenthesis on that. If it was a bracket, then that open circle would be a problem. As I think is going to be the case here. From 5 to 7 is this portion, but we have the problem at 5. So we're going to say no, f of 5 does not exist. When it's an interval of points, people think they need to talk about like all the points. If it's a no, you just need to say where the problem was. The problem was at 5, f of 5 does not exist. And then the last one of those, -1 to 1, we've got brackets. So from -1 to 1, what do you think? No is the correct answer. Unfortunately, this one's a little harder to write. Why can't you just say f of 1 does not exist? It does exist. The problem is the point and the limit don't equal each other. So we're actually going to recopy this answer with one slight difference. Go ahead and just copy it over. There is only one little difference that we're gonna put in there. If your interval is from -1 to 1, and just watch me point to this, I'm gonna try and be left-handed here. You have to approach 1 from which side? You're approaching 1 from the left. So you have to put this little negative in there to show you're approaching it from the left. Cool. That went well. You guys all seemed like you were with me there. Is that like, that's usually the hardest part, is writing all that notation. All right, and then these last two. Find P so that the function is continuous. If you want it to be continuous, that means the two pieces need to do what? Equal each other. We've actually done these before, okay? You're gonna just set them equal. X squared minus 2 equals X minus P. We did these way back when, because this isn't actually calculus, this is more algebra. And then what are we gonna plug in for X? Good, -1, it's where that cut point. Do you remember making the piecewise flip grid thing? We cut it and then flipped them, made them match up. It was like a million years ago. All right, so you're gonna plug in -1 for X. So everywhere there's an X, you're gonna put a -1. And then you just gotta figure that out. So -1 squared, be +1, but then 1 minus 2, -1. And then what would you do to both sides? You would add 1, and what do you get? Yeah, 0. Now it would be 0 equals -P, but you can't negative a 0, so it just comes out to be 0. So again, it says continuous. That means you want to set the two pieces equal. So just take the first one, make it equal the second. Just set them equal. These are the only ones that require any like work or steps. All right, and then you're gonna plug in what number for X? 4. Everywhere there's an X, we're gonna put a 4. And then we're gonna do some algebra. I'm gonna need to do a little bit of this in my head because I'm gonna run out of space here. 4 squared, 16 plus 3 is 19. And then do you remember what we do next? Or what did I call it? You do need to factor, but evacuate. Evacuate, make it all equal 0. So if you minus over the 19, I'm not gonna write -19 minus 19 because I'm gonna run out of space. 4 minus 19 be -15. And so we're gonna actually end up with 2 answers for this. You'll draw your 2 sets of parentheses. And then how does 15 split? Yeah, 5 and 3. To get -2 in the middle. Good, perfect. And so your answers are P equals 5. And on Delta Math, when you go to do your check your understanding, you'll just hit the little button that says add a solution and it'll put another window in there for you. We've done that before.